we are going to continue talking about integration and build up to the point where we can actually do some mechanical operations on this process called integration. Our way into studying integration is often characterized as one of the two big questions of calculus: slope of the tangent line and area under the curve. So our way in yesterday was to find the area under a curve and above an interval, say between A and B. So our way into integration is going to be find the area under a curve and above an interval. Oops, not Unger. So we usually say area under the curve when we want to talk about the area under a curve y equals f of x and above the interval from A to B. So the thing that we need is that area equals length times width. The only thing that we need is area equals length times width. We're using this area equals length times width as a stand-in for any multiplication that we want to do, any application of multiplication that we want to do. Area equals length times width is the same thing when we have distance is equal to rate times time, work is equal to force times distance, force is equal to pressure times area, mass is equal to density times volume. All those things are just extensions of area is equal to length times width. It's just something that we can visualize that involves multiplication. So the trick here with this area under the curve problem is that the length is variable. So what's going on here, what makes this a calculus problem, is that length is variable throughout the width. I want to calculate area as length times width, but when we're looking at the area under a curve and above an interval, the length part is variable. And that's where we switch from multiplication to integration. So the things that we thought about with integration. Integration is multiplication in which one of the factors is variable. Integration is for multiplication but one of the factors is variable. Integration is multiplication, but one of the factors is variable. Side note, this includes the case where more than one factor is variable. If you have $5, you have $1. Integration is multiplication, but one of the factors is variable. Multiplication is repeated addition. Addition is what we do when our terms are all different. Integration is multiplication, but one of the factors is variable. If the length is constant, we get to multiply to find the area. If length is constant, we get to multiply. to find the area. If the length is not constant, we have to drop it down a level to addition. So when the length is not constant, we drop down to addition. If the length is not constant, then we set up an addition. I should have said a sum. But we set up an addition problem. If I have 2 plus 2 plus 2, that's 3 2's. But if I have different values, 1 plus 2 plus 3, this is not multiplication. If all the terms are the same, we get to multiply. If the length is constant, we get to multiply. If the length is not constant, then we have to set up an addition problem. The calculus phase of the operation is to set up an addition with an infinite number of terms, and then think about what that means. Switch from a discrete sum to a continuous sum. So the calculus portion is when we upgrade our discrete sum to a continuous sum. This is where we upgrade the discrete sum to a continuous sum. So that's looking at an infinite number of terms. All right. So yesterday, we talked about how to go about this. Our plan, the first part of the plan, is we're going to set up an area where the length is not constant. So we're going to try to step it down one level so that the length is constant, at least for a bunch of different subintervals from A to B. And then then we get to use multiplication for the areas, and then we just add all them up. So we're going to set up an addition by breaking up the region. So our plan is to assume the function is constant, at least for a little while, so we can use a multiplication to find area. And then just add up all of the pieces of area. So we drew a picture of this yesterday. We started to draw a picture of this yesterday. And I think I just drew a linear function. So we want to find the area under the curve f of x and above the interval from A to B. Our plan is to assume that the function is constant for over some subintervals. So our plan, assume f of x is constant for small pieces of the interval. We're going to assume that f of x is constant for small bits of the interval. That way we can find area with multiplication. The reason that we're doing this is that area is length times width, and I want to use multiplication. So the reason. So That's the reason that we want to do this. So we're going to break the interval up and say, for this small portion of the region, let's say that is a delta x, I'm going to flatten out the function for those small pieces of the interval. And then I'm going to calculate area with multiplication. So I flatten out the function. And I calculate this area with multiplication. Now that the length is constant for this small delta x, I get to use multiplication. And then we just do that for the next one. Now I've got these two lengths. I got this first length is, let's see, let's call this x1. If a is equal to x naught and b is equal to x2, I could say that this first area is f evaluated at x naught, that's the length, times the width, delta x. And I'll just add up the area, f at x1, I use that for the height of this, or sorry, the length of this rectangle, and the width is delta x. So I evaluated the function at one point and another point, and I added up the area of the two rectangles. Any questions? But I'm using different lined paper now, so I ran out of space. I switched paper brands halfway through the semester. It's going to be really crazy. These notepads are also a little bit bumpier, so I'm going to have to be more careful with my writing. So we're approximating the area under the curve with the area of two rectangles. So it'd say that the area is approximately f at x0. That's the constant value that we use for the first rectangle. So that's the length in the first rectangle, and the delta x, that small piece of the interval, is the width of the first rectangle. The delta x is the width of the rectangle. And then we just add the second one. To get the length of the second rectangle, I just evaluated the function at some point, and I multiplied by the width of that rectangle. So this f at x1 is the length of the second rectangle. And delta x is still the width of the rectangle. This misses some of the area that we want. This is missing some of the area that we want. All I did was flatten out the function, and I used that as an approximation. So we can improve the approximation by using more rectangles. So this approximation is missing some area that we want because of the way I drew it. I have an increasing function. I chose the left endpoint. I said f of x is just whatever it was starting off at each interval. I just keep that the whole time. That's it. So we can improve the approximation by using more rectangles. We can improve the approximation by using more rectangles. Since this is a calculus class and the approximation gets better if we use more rectangles, you should see where this is headed. Use more in calculus means use infinitely many. But let's see what happens. Let's draw this picture again and watch it evolve. This should be an animation, but then instead of drawing it, you would just be watching it. So before, I had split the interval in half. And that was what my approximation was. So my approximation was these two rectangles. But I'm missing these big triangles up here. So we can improve the approximation with more rectangles. And all I'm going to do is take the one that I had before, and I'm going to use more rectangles. So now I'm going to, instead of just 2 rectangles, I'm going to split them in half again and use 4 rectangles. So now we can see we're chipping away at the missing area. My delta x is now smaller. Because now I have 4 rectangles, so my delta x is smaller. And now I have more values of x, that I need to calculate. So a is still going to be x0. This will be x1, the new x1. This is new x2. This is x3, and b can be x4. So I had the areas from before. But now I'm going to calculate, instead of calculating, just using these 2 rectangles all the way across, I'm going to use more rectangles. That chips away at the area. So I've made smaller these rectangles in here by putting a more rectangle underneath them. So now I'm going to have 4 rectangles. I used the x0, so I'm going to have my area is going to be approximated by f at x naught times the width delta x plus f at x1 times the width delta x, that's the second rectangle, plus f at x2 times the width delta x, and f at x3 times the width delta x. The width got smaller, but now I'm making up for that by using more rectangles. Because I took what was missing before, and now I've added that to my total area, approximate area. Any questions?
Is there a reason why we couldn't just use the right triangles that are left?
They aren't right triangles if f of x is not a linear function. So if f of x is all curvy, then they're not going to be triangles. One thing that we want to notice down here in our sum is that there's always the width of the interval showing up as a common term. So we want to see what we're doing. We're evaluating the function a bunch of times. And then we're multiplying by the width of the interval. So mechanically, what we're doing is evaluating the function a bunch of times and then multiplying by this delta x. So we could think of factoring out the width of the triangle. So we're factoring out the width of each triangle, and we're adding up a bunch of values of the function. Any questions? All right. So that was the new thing that we didn't get to yesterday. Use more rectangles to get a better approximation of the area. Since we're experienced calculus people, we know that when since the approximation improves with more rectangles, we know that more rectangles in calculus means infinitely many rectangles. That's where this is headed. So this phrase, more rectangles, is going to lead to infinitely many rectangles. In calculus, when we say more rectangles, more rectangles leads to infinitely many rectangles. Just like when we were looking at the slope of the tangent line by calculating the slope of a secant line and say, make the points closer. How close? Infinitely close. Use more rectangles. How many more? Infinitely many more. Any questions?
In theory, when would we stop? Because infinite means I could be making this forever.
Right. So we do the same thing that we did when we were calculating with infinity before. We look to see where things are headed, and then we just go with that. So we just we just gain experience by looking at the things and learning what is it about these numbers that tell us they're headed somewhere? What is the limit at infinity? We can't just plug in infinity. But if we keep plugging in bigger and bigger numbers, are we approaching some value? And that's what's going to happen here, because I could split these down again. I can go from 4 to 8, and I would cut out more rectangles. Then if I went from 8 to 16, I'd cut rectangles out of each one. So geometrically, because everything here is bounded, we can see that this is going to head somewhere to the actual area under the curve by using, so if we do this in an infinite number of times. Right now, we lack the machinery to make that an easy calculation. So right now, if we had to do that, we would just have to do 8 rectangles, then 16, then 32, and see, are these values flattening out? Are we approaching some value? If so, then we can declare that to be the limit. Any questions? Let's pause the video here and come back and look at what kind of takeaways we need moving forward.